Hi everybody, Physics Ninja, and welcome to my tutorial on simple harmonic motion. In this video, we're going to look at the horizontal spring and mass system. We're going to stretch it, let it go, and we're going to be able to analyze the forces. From the forces, we're going to find equations that describe the position, the velocity, and the acceleration. You're also going to understand how to calculate the period, frequency, and angular frequency of the motion of a simple harmonic oscillator like this. We're going to throw in some example problems to make sure you understand how to use the equations. In the second part, we're also going to look at energy in the system, right? We're going to look at the potential energy that gets stored in the spring once it gets stretched, and then gets converted into kinetic energy of the mass once it gets moving. All right. Let's get started. Like with all my videos, if you like it, give it a thumbs up. Consider subscribing to my channel. It's the best way to support what I do. All right, here's a simple harmonic oscillator over here, a mass connected to a spring. And let's just examine the motion. We may have a lot of questions regarding this motion. The first thing we notice is that the motion the mass oscillates back and forth, and this simply repeats itself over and over again, right? We may have a lot of questions about this. One might be like, how long does it take for the mass to go back and forth to complete one cycle? This is something we call the period of oscillation, right? We're going to call that T. That's going to be measured in seconds. Well, how do we calculate the period of oscillation? What factors into the period of oscillations? How would I make the period bigger or smaller, right? Those are questions you might have. What do I have to change? I may be interested in calculating the position of this mass as a function of time. I may also be interested in what is the maximum kind of displacement of this mass. In addition, we're always interested in other kinematic quantities like the velocity and the acceleration. Once you get to acceleration, you're thinking, well, what causes all of this motion, right? Then we get into the questions of forces, right? What kind of forces are acting on this mass in order to produce this periodic motion? Later on in the video, we're going to talk about energy. Like, is energy conserved in the system? And if so, what type of energy is there? You see that the mass is moving, so there's energy associated to motion, right? So this is what we call kinetic energy. But we're also going to see that there's going to be energy in terms of energy stored in the spring. We're going to call this potential energy stored in the spring. And the other question is, well, how do we calculate all these values? All right, so these are all the questions we're going to address in this video. All right, so we start with just our spring mass system here. I've set it up in the horizontal direction. I have a spring that's connected to a wall which can't move, and then I'm connecting a mass, M, to the other end of the spring. Now this spring here has a length, okay? We call this the natural length of the spring. When you just set it up here, for example, on a tabletop, it's going to have a specific length, okay? So that's going to be a parameter that may come into some problems. The other thing, when you set it up on the tabletop, again, once the mass is connected to it and nothing is moving, we call this the equilibrium position, and the mass basically sits at some position, and we're going to call that position 0, okay? And that's the equilibrium position. Now, the other thing we're going to need to define is a coordinate system here, and that's what I have right here. So I'm defining everything here on the right-hand side is going to be a positive value of the position, and everything here on the left-hand side of the equilibrium position is going to have a negative position with respect to the equilibrium position. All right, so the next case we're going to look at now is what happens when I want to do either one of two things. I either want to stretch this spring, or I may want to compress the spring. So let's draw the forces, and keep in mind here, my hand is holding the block, right? So it can't move. So that means all the forces have to balance out. So let's do some of the easy ones, right? For the stretch case, well, we still have a weight for each case here. The block is being pulled down by the earth. What else? We have a normal force. The block is sitting on this horizontal table. So I call that N, force N acting up. That's a normal force. And these are the only two forces in the vertical direction. That case is not very interesting to me. But let's have a look now at the horizontal direction. So horizontal direction, now we have two forces. All right, there is an applied force here. I'm going to call it FA. In this case, because I was pulling the block and now I'm holding it here, right? So there has to be a force like this. In the compression case, as I was pushing the block and as I'm holding it here, there is also an applied force, but it's in this direction. All right. Now, the last force, which is going to be the force of simple harmonic motion, the one we're really interested in, is this spring force, right? When I'm any position here on the right-hand side, the spring wants to bring the block back toward this equilibrium position. So there has to be a spring force here. I'll call it F sub S. In the compression case, again, the spring wants to push the block back toward the equilibrium position. So the spring force is in the opposite direction. Okay. All right. Now let's go have a look, a little bit more detail about this spring force. All right. Now I want to look at something called Hooke's law. Hooke's law is going to allow us to calculate what this spring force is. So Hooke's law is given by this expression right here. It says that the spring force is given by negative this value K multiplied by X. Okay, so we have a couple things that are important about here. This negative sign is important, okay? The negative sign in Hooke's law is important because this is going to be a restoring force. So it kind of tells you the direction of this force, and we'll see that in just a minute, okay? But that's going to be an important quantity here, this negative sign. Now, the other quantity that appears here is this value K. This is something we call a spring constant. It's a property of the spring that we choose. It's going to have units typically of newtons per meter, okay? And it basically tells you how stiff, right? The stiffness of the spring, how hard is it to stretch it or compress it? So for example, a value might be 100 newtons per meter. That might be a value of my spring constant K. Now the other value that's really important is X. Okay, so now X, we're going to go define it here in this figure. We're going to define it for the stretching case and the compression case. X is the displacement from the equilibrium. So in this case, this is the value X. How far is the block from the equilibrium? In this case, look at my x-axis over here. I've stretched it a distance of 5 centimeters. So my x would be positive. Let me just convert that to meters, 0.05 meters. Okay, that is the x value. Notice that it's a positive quantity. All right, how about in the compression case when the block is simply right here? So we're right here. In this case, I go back. How far am I from the equilibrium? I'm a distance of 3 centimeters. However, I'm on the left-hand side of the equilibrium. So my x value in this case is going to be minus 0.03 meters. Okay, so notice that in one case we have a positive x, in the other case we have a negative value of x. So keep in mind, it could be negative or positive. It simply tells you on which side of the equilibrium position we are on. So if I wanted to calculate the force, for example, in the stretching case versus the other case, well, let's have a look. Now, just substitute the numbers, all right? So we're going to have our spring constant. Let's take 100. I still have the negative sign, 100, and this is multiplied by our 5 centimeters, 0.05. Okay, notice we're going to get here minus 5, and that's newtons. All right, let's do it in the compression case. Now we have minus 100 for the spring constant multiplied by 0.03. All right, so my spring, negative, can't forget that. Just told you it was a really important quantity, and now we have, multiply that through, you get a positive 3 Newton force. Okay, so compare these two. What's the difference here? The negative sign will take care of the direction of the force. Notice that the force is always in the opposite direction of the displacement from the equilibrium, right? When x is a positive value, force is in the negative value. And that's exactly what we have right here, right? Look at the force direction compared to this displacement. Look at in the compression case, the force is in this positive direction. My displacement was in the negative direction. Okay, so the force is always opposite of x, of the displacement. Okay, so that's a property of Hooke's law. All right, now let's go back and look at the forces once I remove my hand now, and I want the system to start oscillating. All right, so now I'm holding it here, and what I'm going to do now is I'm going to basically remove my hand. Well, what happens when I remove my hand? Well, a couple things happen. In the stretching case, let's get rid of my hand. Well, if I get rid of my hand, guess what? There is no more applied force. Boom. What about in the compression case? If I go over here and I remove my hand, well, if I remove my hand, I must also get rid of the applied force that was holding it there. Now let's look at what we have here. Okay, we have a net force in the x direction, right? We have a spring force and there's nothing counteracting it. In the compression case, we also have a spring force and we know how to calculate it now, right? All we know is it's minus kx. We have minus kx. This means that we're going to have a net force in the x direction, right? The net force is the spring force. Okay, that means we're going to have an acceleration, right? Think about Newton's second law. Newton's second law says you add up all the forces, right? The net force, that has to be equal to mass times acceleration. So both of these blocks are going to start to accelerate. So now let's go on the next page and look at the dynamics associated with it. And let's get to an equation that allows us to calculate the position of this mass as it oscillates back and forth. All right, we now want to apply Newton's second law to this problem. Newton's second law says that the net force acting on the mass has to be equal to the mass times the acceleration of the block. In this case, there's only one force in the x direction. It's given by Hooke's law, the spring force. That's minus kx. Actually, this is kind of nice. You can get to an expression for the acceleration. All you have to do is bring the mass on the other side. All right. Now, keep in mind, this is true for every single time, okay? It's instantaneously true. So you could really write it like this. The acceleration as a function of time is minus k over m multiplied by the position as a function of time. Okay, so if you know the position at every time and we have our characteristics here of the spring, let's just take this 100 newtons per meter. Now, another important thing for solving these problems is what are the initial conditions of this system? So initial conditions for the mass are, what is the initial position? Okay. The initial position was at time 0. What is my position? In this case, it was 5 centimeters. So 0.05 meters. What else? In this case, I said I released it from rest. Well, guess what? That means that the velocity at time 0 is going to be equal to 0. I forced that by just releasing the block. Now, I don't have to have this. This is just a specific case that I'm looking at. Now, the other thing we notice here is that the acceleration and the position relative to the equilibrium position are in the opposite direction. Okay, so that's really, really important. Okay, because of that negative sign, which came from the Hooke's law. Now, my goal now is to find what is this x of t, right? If I'm able to find x of t, right, I'm able to tell you exactly where this block is for every single time. Okay, one convention that's often used is that if I release it from rest, the distance here, this initial distance, all right, we're going to call this amplitude. Okay, so this is what we typically call the amplitude of the oscillation. And I typically use the letter A in order to characterize that quantity. All right, now let's go look at how we solve this equation right here in order to get the position x as a function of time. All right, so in order to solve the equation, what you have to do here is we write the acceleration as, well, you can write it first as the derivative of the velocity, or how does velocity change with respect to time? And the velocity I can then write as how the position changes with respect to time. And anyway, you end up getting that the acceleration is the second derivative of the position with respect to time. Now, this is kind of getting kind of deeper into the calculus here, but this is my equation that I want to solve. This is a second order differential equation, and typically what they do now is we show you, well, let's try something. We know that the system is going to oscillate back and forth. Let's maybe try a solution that looks something like this. A cos of omega t plus phi. I know trigonometric functions will oscillate back and forth with time, so you could try that solution. So if I take the first derivative to get the velocity, well, you take the first derivative of some trigonometric function like this. First derivative would be a omega comes out of this term over here. And then you have to switch going from cos to sine. And then if I take the second derivative to get the acceleration, I get another omega that pops out. The a in the front is just the amplitude of the oscillation. So you get omega squared here, and then you go back to cos omega t plus phi. All right, so this is kind of useful. So now we go back and we substitute. Well, let's substitute this and this into our equation, my first equation that I started off with, and we're going to get an expression for the solution. So you look first at the left-hand side, is the acceleration. So I have minus a omega squared cos omega t plus phi equals to minus kx, minus k over m, and x was a cos of omega t plus phi. We can see that we have a solution. We have cos omega t plus phi on both sides. Let's just eliminate that. We also have the amplitude on both sides. I have a negative sign on both sides. And look, as long as omega squared equals k over m, and that means that omega, this angular frequency that appears in the solution, is equal to square root of k over m. This is a really, really important expression for simple harmonic motion, for a spring and mass system. Right? The omega is called the angular frequency. Now, angular frequency is related to the linear frequency and also to the period. Remember, angular frequency is just 2 pi multiplied by the frequency measured in hertz. And it's also related to the period because the frequency is 1 over the period. So this is also really important because it allows you right away that you can calculate the period of oscillation of a spring mass system as long as you know the spring constant and you know the mass that is connected to it. You could say something about how long does it take to complete one cycle. All right, now let's put it all together and go back to these expressions and see what they mean. All right, let's just make sure we understand this point here. Here's a key slide here, as you see in the corner, key slide. What I want to do here is, so I've set a mass equal to 2.3 kilograms, and the spring constant is still 100 newtons per meter. Let's go ahead and calculate these values, okay? What is the angular frequency of the oscillation? So this is all you would do. You would do 100 divided by the mass, which is 2.3. And don't forget to take the square root. I put that in the calculator and I get 6.59. That is in radians per second. Okay, what about now the linear frequency? Well, the linear frequency is given by this. It is, again, omega is 2 pi f. So f is omega divided by 2 pi. And we just said that omega was square root of k over m for a simple harmonic oscillator. Okay, so in this case, you would do 1 over 2 pi. And either you put in 6.59 here, or let's just substitute in all the values again, just so we can see the whole thing. Put that in a calculator and you'll get a number of like 1.05 measured in hertz for the linear frequency. The other quantity we want here is the period. Okay, you see that the period is the reciprocal of the frequency, 1 divided by the frequency. So in this case here it would be, well, I'll just write 1 over f. Now, if you take the expression for the frequency, if I just wanted a expression for the period, it would be 2 pi because you do 1 over, and then you end up just reversing this ratio here. So it's mass over k. So for this particular problem, you have 2 pi. We have 2.3 over 100. Put that in a calculator and I get 0.95 seconds. Okay, that is the time to complete one oscillation. That is the definition of the period. Now let's think about how can I change the period of oscillation, right? Oops, let's get the highlighter out. Let's look at our equation for the period here. There's 2 ways I can change the period of oscillation of a simple harmonic motion, right? I could either change the mass, right? If I make the mass bigger, it's going to take a longer period, right? The period is going to be bigger, right? And that makes sense because the object simply has more inertia. It takes more time to complete one cycle if the mass is bigger, okay? So if, let's just write it over here. If the mass goes up, the period of oscillation goes up. That makes sense. What about the spring constant, right? What happens if I make the spring constant smaller? Well, if I make the spring constant smaller, it means the spring is less stiff, right? So if it's less stiff, guess what? It's going to take longer to complete one oscillation, so the period is going to go up. Now, the really, really important thing about the period is that it doesn't depend on the amplitude, right? If A was 5 centimeters, or if the problem was repeated with A equal to, say, 25 centimeters, right? Guess what? The period of oscillation is the same for both, right? Both of these cases have the same period, okay? So let's just make sure that this is really a key point of a simple harmonic oscillator, is the period does not depend on the amplitude of the motion. And that's really, really important. We're going to see other quantities that depend on this amplitude, like the maximum velocity, for example, is going to depend on the amplitude, the maximum acceleration, but the time to complete one cycle does not. All right, so we've spent some time telling you what the angular frequency was, right? Is related to k over m right here, square root of k over m. Now, what about this other guy, right? Well, I said my solution had this phase factor, right? A number that appears in a trigonometric function represents some phase angle. What does this mean? Okay, this guy here is going to be related to the initial conditions, all right? So it depends on the initial conditions of the system. Remember what we said initially. We released our block from rest from 5 centimeters away, but I also said that this initial velocity, that's the velocity at time 0, was 0 for this case. So what does that mean? Well, we have an expression here. If this is my position versus time, I know that the velocity has to be given by this, right? That's the velocity v. So let's go ahead and look at this. So velocity v is minus a omega sine, again, it's the same term over here, omega t plus phi. But how do we satisfy this initial condition here that the initial velocity is 0? What phase value do I need? So substitute at time equals to 0. So we have v at 0. Well, minus a omega, that doesn't change. We have sine. This first term goes to 0, but I'm still left with this phase angle. And I know that I want that initial velocity to be 0. So in this case, so when released from rest, let me just write this out because it's important. In some problems, you may not release it from rest. You may give it some initial velocity. Okay, but in this case, when you release it from rest, the only way I could satisfy this equation here is if that angle equals to 0. Well, guess what? That really simplifies our position. That means you don't even need this term right here. Just get rid of it, right? When you release it from rest, there is no need to include this phase angle right here. And my expressions to describe position, velocity, and acceleration are greatly simplified right here. All right, so let's now just have a quick sketch of what these solutions look like, right? So we can sketch position versus time. So let's start with that one. So it's just a cos of omega t. So again, at time 0, what we have is you started over here at a position of 5 centimeters, right? So this would be 5 centimeters. Now again, I just want to do a sketch. It doesn't have to be precise, but let's just kind of release it. At some point, it's going to go through the equilibrium. So that's when I'm right here. And then it's going to swing and go on the other side. Now this function is just a cos function. Try to draw it as kind of neatly as I can. And then I'll just keep going back and forth. Now, let me just switch the colors here. This will oscillate now between, it'll go back to 5 eventually, right? Once it swings all the way back and forth. However, it will also go down over here. This here, if I did a kind of a quick sketch, down over at the other position here, this should be minus 5 centimeters, right? So it'll oscillate between those positions, all right? this is what we call the amplitude of the oscillation. That's the value A that goes in the front right here. Okay. Now, what else? The other thing that we know about simple harmonic motion is it repeats itself over and over again, which means there is a period of oscillation. The period of oscillation is t, okay? And you can calculate t from this expression because it's related to omega, right? So the period of oscillation, remember, if the omega is equal to square root of k over m, well, the definition of that is 2 pi divided by t. All right, if you do a little bit of algebra here, I got to get the t in the numerator. So it would look something like this, 2 pi. And now if I bring the square root of k over m down here at the bottom, well, what you could do is just to rearrange it, just switch the order here, m over k rather. This is the expression I get for that period of oscillation. How long does it take to do one cycle? Time for one cycle. And again, you can also calculate the frequency in hertz over here. But this is what the sketch looks like for position versus time. Okay. Now, how about this other one? Well, velocity, the next one. Velocity, again, if you know position versus time, the velocity is simply the slope of the graph, right? So have a look. Initially, the slope is 0. So let's do that one in purple right here. So the velocity is 0 right here. You can see the slope is 0. Where else is the velocity 0? Right here. So I should have it here. And right here when I'm back at the original position, the velocity here has to be 0. Now look at this function here. It's minus sine. Sine is something that looks like this, okay? But if I do minus sine, then it has to be opposite. I have to reflect that curve, okay? So it should really look something like this. That's minus a omega sine of omega t. So now again, you can go on this graph and what are the maximum and minimum values of this time? So let's go ahead. This is where you have the maximum. Let's make sure that that makes sense, right? Because if I go on the position graph, where is the slope the biggest? Oh, right here. Look at the slope here is big and it's a positive value. Well, that corresponds to that velocity. Look at right over here. This is the slope. Notice it's negative. The slope is going down and it's a maximum value, right? So that's why it's right over here. So what is that maximum value? Well, again, you can also just look at the function, right? The maximum is when sine of omega t is equal to 1. And that means that my maximum velocity is going to be equal to plus or minus a omega. Okay, so this value right here would be positive a omega, and this guy down here would be minus a omega. That is the maximum velocity that this spring mass system can have. Depends on two things. It depends on how much you've stretched it. That kind of makes sense. And it also depends on the properties of the spring, right? The stiffer it is, and also depends on the mass. Okay, we'll come back to this one in just a minute. All right, the last one we want to plot now is the acceleration. Now the acceleration is what? It looks like the position, except remember it's negative some number times the position. So it should look like the first graph just flipped upside down, right? So it should start over here. Again, it's going to be 0 at the exact same position. When x is 0, acceleration has to be 0. So that has to be here. Has to be opposite, so it should look something like this. When x is 0, acceleration should be 0, and then something like this. So again, it's minus some amplitude cos of omega t. So that's it. You just kind of sketch this out. That's not perfect here when I'm, oops, it's really not perfect. Let's try again. Let's try to at least try to make something that looks like a cosine. All right, not bad. What is the maximum value of the acceleration here? Okay, well, this value here of the acceleration is when x is maximum. Remember, cos is a function that goes between 1 and minus 1. So the maximum acceleration is going to be, say, plus or minus a omega squared. Again, the positive and negative just tells me the direction of the acceleration. Okay, so again, you can relate that back now to properties of the spring and the mass system. All right, let's now that we have at least some understanding of the position, velocity, and acceleration, let's try to solve a problem now relating to a spring mass system released from rest. All right, so let's work through an example problem. It says the movement of a 2.3 kilogram mass attached to a spring is described by this equation right here. We have several questions. So the first question says find the amplitude, angular frequency, phase constant, frequency, and the period for this motion. So this one's a little bit different. Right now we're given this equation, so we have to pick out what the important quantities are. So remember, a general expression for the motion is something like this: a cos omega, sorry about that one, omega t, and then plus some phase constant. Okay, so if you compare these two, you can right away, you can see that this guy right here, this here has to be my amplitude. Okay, so just by inspection, you just say that the amplitude here would be 1.2 meters. All right, what else would we have? Well, the number now that multiplies the time, that is my omega. So what is the number that multiplies the time in this case? Well, in this case, if you look at it carefully, you should be able to see that my omega, the number that multiplies the time, is 1 divided by 2, right? Because if I just rewrite that a little bit differently. So that's just 0.5, and that's in the units of radians per second. All right, pretty straightforward for that one. What about the phase constant? The phase constant is the term that is by itself. It doesn't multiply the time. So in that case, it's this guy. So my phase constant for this motion would be pi over 6. All right, now we're looking for the frequency and the period of motion. Now, how do you find the frequency? The frequency is given by F. Well, there is an equation here that links omega to F. It's this one, it's 2 pi F. So if you know omega, you automatically know the frequency. All right, because you just rearrange this equation. The frequency is omega divided by 2 pi. So in this case, our omega was 0.5. So you have 0.5 divided by 2 pi. All right, put that in the calculator. I should get 0.0796 hertz. You can round that to 0.08 if you wanted to. Okay. That's the frequency. How about the period? Well, once you know the frequency rather, the period is just 1 over f. Okay, so the period here would be 1 divided by 0.0796. And put that in the calculator, you should get like 12.6 seconds. Okay, maybe round that to say 13 seconds approximately. Okay, so now we have the period of motion. Good, so we have everything done here for our first problem. The next question says, well, let's calculate what the spring constant is. So how would you calculate the spring constant for this one? So again, we're looking for the value k. Okay, now for a simple harmonic oscillator, we saw that if you know the angular frequency, you automatically know something else, right? You know this ratio k over m because they're directly related to it. So we were told in the problem that we have a mass of 2.3 kilograms. This means I could calculate k by rearranging this equation. If you square both sides here, what would you get? You get omega squared equals 2k over m. Now I want to get k by itself. So again, we're going to do one more step, bring the mass on the other side. So an equation for the spring constant, if you know the angular frequency, it's simply omega squared times m. So now we substitute our values. My omega was 0.5. Square that thing, and now multiplied by the mass, which is 2.3 kilograms. So the k constant, if I put that in a calculator, I should get 0.575, and that's in newtons per meter. Okay, that's the spring constant. All right, how about question 3? Says we got to find the position now at time equals to 1 second. So basically all you have to do, this is really an expression of x as a function of time. Time is the only unknown in this equation. So all you have to do now is substitute 1 inside this expression. So it looks like this. So at 1 second, well, it's 1.2 cosine of, now it's 1 divided by 2 and plus pi over 6. Okay, I just put that in the calculator, okay, and that is going to allow me to find the position of this object, of this mass, and I should get 0.62 meters is that position. All right, next question. Find the velocity and acceleration at functions of time, as a function of time. So what we're looking for here is an expression for the velocity as a function of time and also the acceleration as a function of time. So again, that is related to, if you know the position as a function of time, the velocity is, you have to take the derivative of this with respect to time. And we did that when we did the problem earlier, right? So how do I take a derivative with respect to time? Again, if you're given just some general function here, it ends up being minus omega a, then sine of omega t plus phi. Okay, and all the values we know, okay? So you can get an expression for the velocity as a function of time. So actually I'm going to go ahead and I'm just going to substitute the values. If I do the omega, it was 0. I have a negative sign, so 0.5. Amplitude was 1.2. Now we have sine, and notice that the omega is the exact same, right? So everything inside the bracket here has to be the exact same. This is t divided by 2, and still plus the same phase angle. So you substitute any amount of time in here, you're going to get the velocity. So here you get minus, what did we get? Minus 0.6 sine of t over 2 plus pi over 6. All right, great. And the last part here was find the acceleration now. Again, the acceleration you get by taking the derivative of this guy. So you get minus omega squared a. And again, you go back now to the cos of omega t plus phi. Okay, again, you could substitute in all the values here. And what you're going to end up getting here should be something like minus 0.3 cosine of t over 2. Plus pi over 6. All right, great job. All right, our final problem now, it says find the values of the position, the velocity, and the acceleration of the mass, but we want the initial value. Okay, so the initial value, what they mean by that is you really want to evaluate at t equals to 0. Okay, that is the initial value of the position, the velocity, and the acceleration. So pretty straightforward, right? In terms of a function, this is what you do. You substitute t equals to 0 in that equation. So it becomes pretty straightforward. This is 1.2 cosine. Now the term that multiplies time goes to 0 because you've substituted 0. So you're left with pi over 6. We put that in a calculator. You should get 1.04 meters. The initial velocity, again, substituting 0, this simplifies to 0.6. Sine of, again, pi over 6. This gives me minus 0.3 meters per second. And the last one now is the acceleration. Oops, this is at time equals to 0. Minus 0.3 cosine of pi over 6. I'll put that in a calculator. I think you get minus 0.26 meters per second squared. All right, so this was kind of a nice problem. It was different from the previous case in that now we had this phase angle, and whenever there's a phase angle, it automatically means that you're going to have an initial velocity that is some number. It's not going to be 0 because we have this phase angle in this specific case. All right, I want to consider this spring again, and we're going to now look at the work done by the spring force when I'm first stretching it, right? I started the block at equilibrium, and I grabbed it, and I pulled on it, right? As I'm pulling on it, remember, I'm applying a force to the right, and the spring is providing a force to the left. All right, but I'm doing work, and there's also the spring force that is doing work on the mass. Now, in order to understand this and how to calculate it, okay, I'm going to first look at gravity and see how you would do it for gravity, okay? For gravity, I'm going to consider a mass here that's on the ground. It has a mass of 2.3 kilograms, and I want to lift it up and place it on the table. For me to lift it up, I have to apply a force, okay? And I apply a force, and gravity is also acting on the mass as I'm lifting it up, okay? How much work is done by my force and how much work is done by the force of gravity during this process? All right, work done by gravity is simpler than the spring, okay? Because remember that the force of gravity is a constant force. And whenever you have a constant force, things are a little bit simpler, okay? Let me just write that down. Let's do the free body diagram on the mass. I have a mass mg acting down, and I have an applied force. I'm lifting it, right? So I have an applied force that's opposite of that. All right, first thing we're going to do now is, if the force is constant, to calculate the work, there's really two ways to do it. If the force is constant, the work done by gravity or any constant force is the magnitude of the force, in this case the force of gravity. It's the magnitude of the displacement, and then multiplied by cos of the angle between both of those, between the force and the displacement. Now think about the displacement delta y in this case. Delta y has to be like this, right? And if my force of gravity is acting down, that's mg, guess what? The angle between both of those, this angle theta here, is going to be 180 degrees. All right, cos of 180 degrees is equal to -1. So now we substitute in all our values here, right? The force of gravity, the magnitude is mg. The displacement is actually the height, right? That's the magnitude. That's how far we're moving. And then, like I said, cos of 180 is right here. So cos of 180 is -1. So this becomes minus mgh. That is the work done by the force of gravity. We could substitute our values here. This is 2.3, 9.8, and the height was 0.8 meters. So that means that the work done by gravity is going to be minus, put that in the calculator, you get 18 joules of work done by the force of gravity. Well, how much energy did it take me to lift this mass? For that, I'm looking for how much work was done by the applied force. Okay, my applied force, the work done is simply minus the work done by gravity. Okay, so in this case, it takes me 18 joules of energy in order to lift this mass and place it on the table. Now, for the spring force, we cannot use this equation, okay? It's very, very important. So not for springs. Because the spring force is not constant, right? That was one of the requirements to use this equation. So in order to calculate the work done by the spring, we're going to do it a little bit differently. All right, to calculate the work done by the spring, we remember that our spring force, let me go ahead and change the color here. The spring force was given by Hooke's law was minus kx. And the key point is this is not constant. To calculate the work done by a force that is not constant, what you have to do is we have to integrate. Okay, you have to calculate the area under the curve of the force versus distance. In mathematical terms, this is what it looks like. You integrate from some initial position to some final position. In this case here, the initial position is right here. That is when x equals to 0. And my final position is going to be right here. X final is going to be equal to 5 centimeters, 0.05 meters. All right, but let's get algebraic expression for it. So we get the work done. Again, this is by the spring force. So I'm going to use spring force in the integral. I'm going from an initial value to a final value. Now the force is given by Hooke's law. You just substituted it here. And you multiply by the little element of displacement, dx. I can take out the constant terms. So I take out minus k. Those are constants. They don't affect the integral. And again, now I just rewrite this as x dx. All right, if you've taken calculus, this is actually a really easy term to evaluate, okay? The only thing you have to do is just increase the power. So it's x squared over 2, and you have to evaluate that between those limits. All right, so you get minus k, and now I'll take the 2 out, and now I just put in these limits over here. So I get x final squared minus x initial squared. Now to clean up this expression a little bit, let me just distribute this negative sign in the front. All right, so the final expression for the work done by the spring is going to be kx initial squared divided by 2 minus kx final squared divided by 2. The initial position was 0. Forget about that term. For this particular problem, we're left with minus 100 over 2. My x final 0.05 squared. The work done by the spring in this case is going to be minus 0.125 joules, a little bit of work done by the spring. Notice that the sign is negative again. Now, why is it negative? Well, again, if you go back to my force picture, right, the force of the spring is this way, and guess what? My displacement, right, delta x is that way, right? So you have this 180 degrees. Although I can't use that equation to find the value of the work to determine whether it's positive or negative, that still works, right? Force in one direction, displacement in the other always gives you a negative value for the work. But that means that my applied force, the work done by the applied force, is simply minus the work done by the spring. That's the easiest way to calculate it. So in this case, we get 0.125 joules of energy required by my applied force in order to stretch that spring. Notice that it does not depend on the mass for this case, right? So whether it's 100 kg or 200 kg or 2.3, right, the work done by the spring only depends on the properties of the spring and how far you stretch it. All right, in the previous case, we showed that the work done by the spring could be written as this, right? It's the difference between these two values. Okay, so now I want to introduce the concept of potential energy stored in the spring. Okay, we're going to call the potential energy stored in the spring, I'm going to give it a letter U. That's typically the letter you use for potential energy. And to remind myself that it's by the spring, I'm going to use this subscript right here. All right, and the definition of spring potential energy, it's going to be pretty straightforward. It's going to be 1/2 kx squared. Okay, so k again is the spring constant and x is the displacement. The same variables that appear in Hooke's law in the force equation appear over here in our spring potential energy. This here is measured in joules, okay? Now, if you go back and think about this equation, then if I use that new definition of potential energy of the spring, that means you could calculate the work done by the spring as being equal to, well, look at the first term. It looks like a potential energy term. I would call it the initial potential energy stored in the spring minus the final potential energy stored in the spring. Okay, a lot of times, sometimes they switch the order of these things. And if you do that, you can write it as minus U final minus U initial. So this is typically what is done when you're talking about certain types of forces that are called conservative forces. You can write the work done by any conservative force as minus the change in potential energy of that system. So this is a really important equation right here. It's another way of calculating the work and using our definition here of the spring potential energy. So now we're going to look at the energy conservation during this periodic motion, okay? Because again, we have our mass that's oscillating back and forth. So if you look at our equations, there's some values when you have a lot of spring potential energy, right? Whenever our x value is big, I have a lot of spring potential energy. For example, down here, when the block goes through the equilibrium position, well, the spring potential energy is actually equal to 0. Over here in this initial configuration, the spring potential energy would be 1/2 kx squared. Okay, so you have a lot of spring potential energy here. And over here, when it goes through the equilibrium, I have 0 potential energy over here. Now, one thing to notice about this equation is also has a squared factor for this variable x. So that means when it swings back onto the other side, for example, when x equals to minus 5 centimeters, guess what? The potential energy that I'm going to have is going to be the same as I had right here initially. These two values here have to be the same because it's the value of x that gets squared. So whether it's positive or negative, you're going to have the same amount of spring potential energy on each side of this equilibrium position. All right, we consider our block again. Again, I'm going to release this from rest, which means that the initial velocity has to be equal to 0 meters per second. From this graph here, again, I have an amplitude, which is this initial x value, right? That's x at time 0 is something we call the amplitude of the motion. In this case, it's 0.05 meters, rather. Clean that up. All right, now we know that if it starts from 0, let's think about all the energy terms we have now, okay? That means initially I have a lot amount of stretch. I have 5 centimeters. So we just saw now that means that we have initially some spring potential energy, which is going to be equal to 1/2 kx squared. Except now the x value takes on this 5 centimeters, right? So we have 1/2 ka squared. Now, what other type of energy is there typically? Well, when this mass starts to move, right? We know there is energy associated to motion, and energy associated to motion is something we call kinetic energy. And kinetic energy is 1/2 mv squared, right? It's always the same formula. Now, initially, there is no kinetic energy at this time, right? So we say there's 0, okay? Now, if I go ahead and I add both of these together, right, if you go ahead and sum both of those, you get the total mechanical energy of the system. Okay, so the total energy in this case here would simply be, at any point, it's the spring plus the kinetic, but initially what we have is 1/2 Ka squared. Okay, that's the total energy. Now, in cases where there is no friction over here, imagine here we say there's no friction between the block and the ground. So in that case, the total energy of the system has to be a conserved quantity. Okay, what that means is that at some point, we know that the mass starts to move. At some point, it's going to be located right here at this position at some other value of x, right? So if you wanted to write the total energy at this second position, well, I would simply say that the total energy has to have some kinetic energy and plus some spring potential energy. The kinetic energy of the mass is 1/2 mv squared plus, again, now the spring potential energy is 1/2 kx squared, where x now is this value. It's no longer this initial amplitude that we started with. Now, if energy is conserved, guess what that means? That means that this value here has to be equal to what? Has to be equal to the initial energy of the system. And the initial energy of the system is right here. So you have to have this equality here. 1/2 Ka squared has to be equal to 1/2 mv squared plus 1/2 kx squared. Now, this equation is actually really useful because it does give us another way of calculating how fast the object is moving, because notice I have the speed here for every single position of this mass. So what you'd have to do now, if I wanted to get an expression for the speed, is first of all, you cancel out the 1/2 terms because they appear everywhere. Now I'm going to bring this kx squared to the other side. So this is what it ends up being. So you get 1/2 mv squared by itself equals to 1/2 Ka squared minus 1/2 Kx squared. Now we do some algebra. I want to get speed or velocity here by itself. So now I have to divide through by the mass. So let's go ahead and do that. So I get rid of it here. That means I have to add it over here. And I have to add it over here. Now I can also factor out the k over m terms. And I'm left here with a bracket with a squared minus x squared. And the last thing I have to do if I want my expression for the speed is I take the square root and I get a plus or minus. Oh, I get k over m. And here I get a squared minus x squared. Notice you get two solutions here, right? I get a plus or a minus. Again, that's because you're going to get two solutions because sometimes the speed of an object moving this way is going to be the same as the speed of an object moving the other way when it comes back. Remember, this motion is periodic here. So this is kind of a useful equation here that allows you to calculate how fast an object is moving for different positions along this axis. Yeah, another way that you can show that the energy is conserved is by just doing something like this. You write the total energy as being 1/2 mv squared plus 1/2 kx squared. Okay, and now we're going to use our kinematic equations that we had before. Remember, I was able to write the position as something like this, a cos of omega t plus some phase factor. And I was also able to take the derivative of this with respect to time. So you get minus omega a sine of omega t plus phi. All right, now what you can do, well, look at now you can simply substitute my expressions here. I have x that goes in here, and I have v that goes over here, right? So let's go ahead and write the total energy then. So you get 1/2 m. The speed I write as this term squared, so it's minus omega a sine of omega t plus phi. Square that term, and now plus 1/2 k, and now you have to square the x value. A cos of omega t plus phi. All right, and don't forget to square it. Now we have to do a little bit of algebra here. Let's square those terms and see what we're left with. So we get 1/2 m. This becomes omega squared a squared. This looks complicated, but just bear with me for 1 minute. Sine squared of omega t plus phi plus 1/2 k. Again, now here I get an a squared, and again cos squared of omega t plus phi. Now, there is a simplification that comes here, because remember, for any simple harmonic oscillator, the omega was something like this, square root of k over m. And if I use that definition and I substitute that in right here for this definition, what we're going to get here is a simplification that our total energy is 1/2 m. Okay, the omega squared here becomes k, let me clean that up, k over m. A squared sine squared omega t plus phi, and let's just rewrite this other term here. Now this simplifies nicely. This is where the magic happens. Right, the masses here cancel out. You have mass on each side. And now look at these terms. They look exactly the same, right? They have 1/2 ka squared. Here you have a 1/2 ka squared. One of them has a sine squared and the other one has a cosine squared. But if you remember from math class, there is a very well-known identity of sine of some angle squared plus the cosine of some angle squared is equal to 1. So guess what? You can simplify this, that the total energy at the end has to be 1/2 ka squared. And again, everything here is going to be equal to 1, right? Because you have sine squared of something plus cosine squared of the exact same term. So we use that trigonometric identity in order to simplify this. It's equal to 1. So at the end, we don't even write this term. The total energy, just get rid of this term, and is equal to this, okay? And that is all spring potential energy in this case, okay? All right, I want to say a few things about showing graphs when you talk about the energy in simple harmonic motion. Again, we want to plot, there's typically 2 types of graphs you have to need to know. The first one is energy versus the position. All right, let me go ahead and denote a few positions that we know. So there's position 0. There might be when x equals to positive a, like in this case over here. And then we know it swings all the way to the other side. So x might equal to minus a on the other side. All right, there's 3 things we have to know, right? There's the total energy. I'll do that one in black. We're going to do the kinetic energy in red. And I'll do the spring potential energy US in blue. So this guy, we know the equation. It's 1/2 kx squared. This one, we know the equation. It's 1/2 mv squared. And this guy we said was 1/2 ka squared. Now, if I'm plotting this as a function of position, well, let's start with the spring potential energy. The spring potential energy is 1/2 kx squared. Look at that x squared term. That means when I'm at x equals to a, somewhere over here, I have some spring potential energy. When I'm at 0, when x equals to 0 right here, I have 0 spring potential energy. And when I'm at x equals to minus a, I have the same amount of spring potential energy that I had initially. Now, how do you connect those points? Now, you don't connect them with a straight line because it's an x squared dependence right here. So the x squared looks like a parabola. So if I'm plotting energy versus position, I should have a symmetric function. I'm just trying to sketch this quickly here. Should look something like that. All right, what about let's do the total energy next. The total energy is 1/2 ka squared. So here's the total energy over here. Here's the total energy over here. Well, everywhere I plot it, it has to have the same value, right? It doesn't matter where you go, anywhere on this, between -5 and +5, I'm going to have the same amount of total energy. So what we're going to do now is, instead of drawing a whole bunch of points, let me just draw a straight line. This straight line here represents the total energy. The first one I drew here, this was the spring potential energy. All right, now we have to use some thinking. Now, how do we plot the kinetic energy using an energy versus position graph? Well, there's a couple points we should know. Okay, first of all, if I'm releasing it from rest, it means that initially there is 0 kinetic energy right here. And also we know that over here at this end, the block instantaneously stops, right? So we also have kinetic energy, which is equal to 0. So I could put that point there. Now, when it goes through the center, guess what we have? We have all of the spring potential energy gets converted into kinetic energy. So all of the energy then becomes kinetic. Now, if we write down this equation here, right, the total energy equals to the kinetic plus the potential, the way that you get an expression for kinetic energy is doing something like this. So it's E total minus US. So E total minus US should look like this, should look like a parabola that is inverted. Try to sketch it nicely here. It should look something like that. Okay, and then again, you can substitute the values to show that. So here you get 1/2 Ka squared, and then minus 1/2 Kx squared. So here I have a minus Kx squared. Negative in front of an x squared is an inverted parabola, okay, if you remember that from math class. The second type of graphs we're typically asked to do for these types of problems might be energy versus time graphs. Now we're going to plot it for one complete cycle. So this is going to be halfway through. Maybe I can also do like a quarter of the way through, 3/4 of the way through, one full period. Now the easiest one to do again is the total energy, because the total energy should look like a straight line because energy is conserved in this system. All right, let's think about the spring potential energy. Well, spring potential energy here, if I wanted to write it as a function of time, you need to substitute the x as a function of time, which is a cos of omega t. But again, you have to square that value. So the spring potential energy is 1/2 K a squared cos squared of omega t. Now cos squared looks a little bit different, so it's going to start off here as being the same, but once I'm halfway through, once I'm on this other side here, right, I have the exact same amount of energy, spring potential energy, as I started with, and then eventually I go back over here. Now the other points to consider are when I'm going through the equilibrium position. Here I should have 0, right? I should have 0 here, and also, oh, I said 3/4 and I wrote 3/3. That's not good. All right, and now when I go back, when the mass oscillates back and goes through the equilibrium, I should also have 0 over here. Now a cos squared function, now you got to be careful when you draw this here. It should look something like this. Again, this is just a sketch. Oh boy, oh boy, we could do better than that. Sometimes you have to go a little bit faster. With my pad, it's a little bit tricky. You could take a proper plotting software and do a much better job than I'm doing here. Now the kinetic energy, again, some points are very easy to plot because this one has to be 0. Once it goes through the equilibrium here, the kinetic energy should be a maximum value. And then it should be 0 once I'm all the way on the other side. All right, this is at t/2. This is at t/4 and 3t/4. So here I'm going the fastest speed possible. And over here, I'm going back to 0. Now it should look, again, if I add the blue line to a red line, I have to have a constant. So it kind of has the same type of shape, just kind of inverted. Let me try to do a better job here. So it's like there's 2 cycles of energy, right? When I'm going from one complete cycle of position oscillation, right? So these are kind of the 2 types of graphs that you might see in simple harmonic motion problems. All right, here's another problem now. We're going to deal with trying to use energy in order to solve these questions. So we have a 3 kilogram mass here that has an amplitude of 4 centimeters and a period of 2 seconds. All right, so let's see what we have. Let me just kind of draw a few things here. Just the amplitude is A, that's 0.04 meters. And the period, they tell me, is 2 seconds. Okay. So first question says, what is the total energy? Again, the total energy is equal to, well, when there's no kinetic, when I'm all the way at the edge, it's 1/2 Ka squared. All of the energy is stored into spring potential energy. All right, so, well, I don't know the spring constant, right? So I'm a little bit stuck right now. All right, so sometimes they don't give you all the information. I know the amplitude, but in this case, I don't know the spring constant. But they do give you other information, right? So if you do know the period, remember that omega is equal to square root of k over m. And our omega is related to the period. It's 2 pi over t. So they've given me this. So guess what? I can do a little bit of calculations in order to calculate what k is. Right, so let's think about it. So we have k over m. If I square both sides, guess what? I get 2 pi t, and I'm going to square that. And as long as I bring the mass over on this side, I have now an expression for the spring constant. And now it's in terms of some of the variables that are provided in the problem. I know the mass, I know the period. I can calculate this as a number. All right, so what I'm going to do here at the end is just substitute this entire expression here for k. So it's m. Here I get 2 pi divided by the period, and I square that. And now multiplied by the amplitude. The amplitude was, I'll just call it a squared. And now we'll put in all the numbers. Right, so you get 1/2. The mass was 3 kilograms. Here we get 2 pi divided by the period, which is 2. Square that, and now 0.04, and square that thing. All right, we put that in the calculator, and we get something that's around 2.37 multiplied by 10 to the minus 2 joules. That's the total energy. All right, the next question B says, what's the maximum speed? All right, if you think about this harmonic oscillator, the maximum speed is always when you go through the equilibrium position. Because if you think about the energy, we have E total, which is equal to kinetic plus potential. Okay, the kinetic is 1/2 mv squared, and my spring potential is 1/2 kx squared. And this here has to be equal to E total, the number we just calculated. Well, guess what? When this term here equals to 0, that's when all of the energy gets converted into kinetic energy. That is when you're going to get the maximum speed. Okay, so we could just get an expression now for maximum speed. We get max speed. All right, we have to isolate. You bring the 2 on the other side, so you get 2 multiplied by E total divided by the mass, and now you take the square root. All right, I put that in a calculator, and I should get something like 0.126 meters per second. All right, here's the last problem. They want to know at which position is the speed equal to half its maximum value. All right, for this problem, first thing we're going to do is give myself a little bit more space because I can already tell the algebra is going to be a little bit messy. So what I want to know is when V equals to V max over 2, right? What is the X value? That's what it's asking for. So it's got to be somewhere between plus or minus 0.04 meters. Now, the way you do this using energy, well, we're going to write down our energy statement. Energy is equal to, again, this is total, equals to kinetic, 1/2 mv squared plus 1/2 kx squared. All right, my goal is to find x. I know what E total is. I calculated that in the first part. And now what I want to do is I want to set the speed equal to V max over 2, right? I want to square that, plus 1/2 kx squared. All right, now you could just substitute in numbers right away. You do need this spring constant, but I can calculate that easily using this expression. But for now, let's just kind of do some algebra and try to simplify it. What I'm going to do with this kinetic energy term is I'm going to expand this. So I'm going to bring the 4 that appears here in the denominator once I square things. I'm going to bring that to the front, and you'll see why. This term here that becomes 1/2 m V max squared, again, plus some spring potential energy. Okay, that there is the E total. Now, remember what this was equal to. We just did a problem where this was actually equal to the total energy. So what you have here is the total energy on the left-hand side, and here you have 1/4 of the total energy here. So if I bring this on the other side, it means you're left with 3/4 of the total energy of the system has to be equal to, oh, that's what's left for the spring potential energy. Now you could factor out a 2 from each side, and you can get an expression that says that, well, x is equal to 3/2 E total divided by that spring constant, and then take a square root, and you get plus or minus. There's two solutions. It can be on one side or the other. All right, now in terms of what can we do now? Well, you could try to eliminate k by using this expression, but that gets kind of messy. What I'm going to do instead is I'm just going to substitute my expression for E total that I used in the first problem. In the first problem, I said E total was 1/2 Ka squared, right? That was E total. And then I have to divide by K, right? Because that's what appears here in the denominator. So you see that the spring constant actually doesn't matter for this problem. It ends up canceling out here. So at the end here, you're left with just some numbers that you can substitute into the calculator. We're left with plus or minus square root of 3 over 2 multiplied by a. You put that in the calculator. Plus or minus square root of 3 over 2 multiplied by 0.04. And lo and behold, I should get 3.5 centimeters. All right, so 0.35 meters would be my position x, where my speed is equal to half the maximum speed. Okay, so this is kind of a nice problem dealing with energy in simple harmonic motion.